So, magnetism. First, what's the most basic thing you know about magnets? Something basic. Poles. Good. It's got to have two poles. Okay, it's got to have two poles. Now, if it's got two poles, it's got what kind of poles? What are they called? North and south poles. Now, what's interesting about magnets that's different from the electric charges is that electric charges, you could have just a positive charge or just a negative charge by itself. But with poles, they have to come in pairs. You always have to have a positive and a negative end for poles. So as a result, what we're going to notice is that even if we cut a magnet in half, we're still going to have poles that result. So draw yourself a magnet with north and south. You can draw yourself a magnet with north and south. Cut it in half by putting like a squiggly line down the middle. Okay, cut it in half. Those two pieces that result are both magnets now, with positive and negative ends to them. So let me show you what I'm saying. Okay, here's all your quiz back, all your quiz file in front. Just so you know. Guys, relax. So we take it, we cut the magnet in half. Listen. As a result, we get this. There's one piece. Here's the other piece of the magnet, right? That's what it would look like if we were able to just snap it in half. Now, magnetic domain theory tells me that a magnet is really consistent of an infinite amount of small magnets inside of it. And remember, magnetic domain theory told me when there's a magnet, all the alignments of all those domains are toward the north end. That's the whole concept of a magnet. So when I break this magnet in half, I still have a ton of little magnets, really, all pointing this way. So you still have all these arrows all pointing to the left. Every arrow is pointing to the left. So what that means is this, and this is the interesting part. The magnet that you get, or the magnets you get as a result, still have a north and south end to each of them. But we just have two magnets now. Okay, there's still a north and south pole, but they're just two smaller magnets. The alignment doesn't change just because you break it. They're still aligned the same way. If they're still all pointing left, then both magnets have a north end on the left of them.
Is the strength of the magnet the same? Or would it be smaller if the magnet itself is small?
The overall magnet would be the same, but each piece would have a different strength.
Okay. Would it cut in half exactly, or would it just, is that not how it works?
I don't know, to be honest. That's a good question. I'm not sure if it would be exact, but it would definitely not be the same strength. But the overall magnet, if rejoined, put back together, would be the same strength as the magnet it was. And what would happen is you would have some attractive force here, right? Because what happens? Opposites attract. So although you snap a magnet in half, and you can do this, if you've got a bar magnet simply has a north and a south end, snap it in half. It will want to rejoin. It'll want to go back together. Okay, if you snap the actual magnet in half down the middle, it'll want to reattach there. But if you separate them enough, you would have two smaller magnets now as a result. Okay, that's basic stuff we learned. What else? We learned that magnetic fields exit the North Pole and enter the South Pole. So really, here's what we have. If I'm drawing the magnetic field lines, it would look like this. Coming out of the North Pole and into the South Pole. Now, those magnetic field lines don't disappear in the magnet. They continue through the magnet. But that's kind of what those little blue lines really are. Those little blue lines are magnetic field lines, really. But really, this continues, right, like this. Straight through the magnet, across. This one continues. Straight through the magnet, across. So we get this kind of a looping, right? This looping, which is similar to what we saw with positive and negative point charges. Similar, not exact, similar. That's the idea behind how a magnet is physically working. Now, we also talked about electromagnets in chapter 21. What was the concept behind an electromagnet? The general concept. Just the general concept.
When you can take a wire and and then you run an electric current through it, it'll create an electric field around the wire.
So any wire that has a current flowing through it, let's say this is a wire, there's a current flowing upward. Any wire that has a current flowing through it has been determined that it always, or it has been determined that it always produces a magnetic field. Always, always, always. You take your thumb, you point it in the direction of current, you take your fingers, and curl is a right hand rule. Do not, I know there's some lefties in the class, don't use your left hand, look at the opposite result. Right hand rule. Thumb goes in the direction of the current, fingers are the direction of the magnetic field. So in this case, the magnetic field would be coming out of the page over here and into the page over here. It would be kind of looping like this around it. And think about the way your fingers would curl. Your fingers would curl just like this. Out of the page on the left and into the page on the right. This was the first of two right-hand rules. The second right-hand rule had to do with a charged particle moving in a magnetic field. This is a current traveling through a wire producing a magnetic field. So again, like this, okay? Like this, curling around the wire. Now, what Paul had mentioned was doing something with this wire to make an electromagnet. What can you tell me about this? The electromagnet specifically. How would it differ from what we're seeing on the board here? How would that differ? How does electromagnet differ? Say again? Yeah. So electromagnet is really taking a solenoid, which is looped wire, and putting either a magnet or a ferromagnetic material in it. So it's just missing a solenoid. Okay, that's what Marianne is mentioning there. So let's take a look at what a solenoid is first. So a solenoid is like, imagine if you have a wire traveling like this, and it starts to loop, and loop, and loop, and loop, like this, over and over and over. Okay, so let's say that's what the wire looks like. Here's the current coming in this way. If this were to happen, every time there's a loop, the magnetic field strength is increasing. And what's going on here is you take your right hand, follow the direction of the current, follow the direction of the current, and your fingers are going to show the direction of the magnetic field. Well, as they loop, what you'll notice is they keep looping like this, over and over and over again. So your fingers will point in the direction of the magnetic field, and this will, in the end, produce an electromagnet. So the concept is that you take some sort of a ferromagnetic material, call that like a core, some sort of an iron core inside of it. The magnetic field strength from the wire makes that iron material into a magnet, which makes this whole thing into an electromagnet. Okay, again, an electromagnet. So what happened here is, God bless you, is this would, in the end, become analogous to a magnet itself. Okay, it would produce a field coming out of the end and into the other. Let me visualize this for a second. It's going behind the wire. As it comes through here, come out that end. So the field would look like this. The magnetic field would come out this end and curl back around. Out this end and curl back around. And the reason I know that is because if I take a look at this wire and I go like this, my fingers, so they're going to start like this, right? And they start to curl around. My fingers are going to face back out this way. Even as I turn around the wire, look at my fingers the way that they're facing. Okay, as I curl them, they're always facing out this way. So this means that the field is going to come out this end and back into the other. So as a result, this pretty much becomes like a North Pole and a South Pole situation. That's the North Pole of the magnet on the right and the South Pole of the magnet on the far left. Steph?
What type of questions do you ask this? Or like what?
Theoretical, free response, multiple choice, not mathematical really. I mean, you should know several things mathematically, that if you increase the current, the strength of the magnetic field goes up. So if you have more, say you have a battery and you can get a stronger battery, you get a stronger electromagnet. if you increase the number of coils. Kev, do you have yours with you by any chance? Is it home? Okay. If you increase, because I was going to use the demo of the coils.
The old one, but it doesn't work.
It does, is it in the closet?
Yeah.
Where is it?
3 seconds to go on.
In the bag cabinet, or where is it exactly?
In the bag.
Do you have some coils looped anywhere or no?
I think it's on the wood website.
Alright, it's not a big deal if I can't find it. I'll keep going. Oh, here it is. Alright. So, for example, so you can see, Kevin and his science club group were working on this electric car kit, and they were trying to come up with something that would spin. So this is what we're talking about. See how the wires loop like that? The number of loops, the more loops you have, the stronger the actual field produces. So, for example, here, looks like there's about 10 to 12 loops in the wire. If you double the amount of loops, you double the field strength. They're directly related to each other. Now, these wires, a current goes into the wire, goes through the wire, out the other end. If you increase the current going into the wire, you also increase the magnetic field strength. But the loops are literally how many times it circles up. Alright, now what about magnetism as far as section 21.3, where we looked at magnetic field strength of a charged particle in a magnetic field? E in the Q thing. Yep, that's right. So here's our this is section 21.3 now. Here's our formula. B equals F magnetic over Q times V. Q is the charge, V is the velocity, F is the force felt, B, now this is what the other class kept misconstruing, so please make sure you either jot this down or know it. B is the field strength. Okay, the field strength. F is the actual force. So you have magnetic field strength for B and magnetic force for F. And they're directly related. If the field is stronger, the force felt is stronger. Okay, they're directly related. That's obvious by looking at this. Now, some things to notice. Formula is given this way in your text and in a few other things as well. But you can easily solve for Fm by multiplying by QV on both sides. Okay, and this might be a way you might use it or interpret it on the actual test. Okay, using that bottom formula there. So what this tells me is the following. The force felt by the particle is related directly or jointly, really, to not only the field strength, but also the charge of the particle and the velocity of the particle. So if the particle has a higher charge, it's got a higher force felt. If there's a higher velocity, higher force felt. If there's a higher field strength, higher force felt. Okay, let's get into some mathematical examples of this, because we did a whole nother right-hand rule here. Okay, we did a whole nother right-hand rule. And the right-hand rule told me in this case, put your fingers in the direction of B, put your thumb in the direction of the velocity, and the force will be the direction your palm faces. Remember, this is the force felt by a positive particle. A positive particle. Those are the three rules to the second right-hand rule. Again, the first right-hand rule is simply take your thumb, put it in the direction of current, your fingers wrap around the wire, showing the direction of the magnetic field around the wire. That's a bonus that nobody did, which is fine. That was a tougher bonus. But if you want to still do that, feel free to. This right-hand rule, though, we have several things going on here. Fingers go in the direction of the magnetic field. Thumb goes in the direction of velocity. Palm faces the direction of the force felt on a positive particle. So the other class was confused because they kept asking, well, what if the field is this way and this is different? It depends on the problem. So give me a scenario. I don't care what it is. Give me a scenario. Tell me which way the field should aim.
The field is downward.
Downward. All right, so let's pause and let's start with that. So there's a field of 2 Tesla acting downward. So you start with this. Okay? Field lines are usually drawn, many of them. You know how we draw field lines usually? So right away already, your fingers should be facing down. Down. Not into the page. Into the page are X's, man. We'll talk about that in a minute. So fingers are facing down. Okay, yes, like a dog. Okay? So fingers are facing down. Now, which way is the particle traveling? You can tell me options. Left, right, up, down, out of the page, or into the page. It doesn't really matter. Any example will work. It depends on which way we're looking on the test. Out of the page. Okay. So let's say that the velocity is out of the page. How do I draw out of the page? With a bunch of dots. I heard dots from somebody, but guys, remember, if I throw a dart at you and it's coming out of the page, you'd see the tip of the dart, right? It would look like a circle. If you throw a dart at a dartboard, you see the tail, which looks like X's. That's how you remember which is which. So the velocity is out of the page. You should really draw yourself a diagram of this on the test. Even though it's a word problem, you should probably do that. So we said the field strength was 2 Tesla. Right, 2 Tesla did I say? The velocity, let's say, is 10 meters per second. So again, let's continue doing this. Ready? So fingers are down. Which way should the thumb be facing? Yeah, towards you. So it should be like this right now. It's kind of a weird, awkward position. Okay, like this. Again, fingers are down, because that's B. Velocity is out of the page, that's your thumb. So this is what's happening right now. Which way is your palm facing? To the right. So a positive particle would be pushed to the right. What about a negative particle? Push to the left. Okay? So I'm going to draw myself a little particle now in red. Draw yourself a particle right here. We'll say that this particle is positively charged. Yes. How would the picture look if the velocity was going up? That's a good question. Let's go over that. So remember, folks, that the velocity and the actual field can never be in the same direction. So the velocity will never be up or down if the field is up or down. You couldn't do it. Right? Because remember, think about your fingers. Don't these make a right angle always? It wouldn't work. Okay? You will never get an example where the field is down and the particle is down, because it wouldn't move. Okay? If it's moving down, it doesn't have any effect on it by the field. It's a good question. All right, so in this case again, ready? Field is down, thumb is toward us, force is to the right. Force is going to be felt to the right. So I could technically draw the force on this like this. That's the way the force would be felt. Now, if this particle is in this orientation, in a uniform field like it is, what will happen to it if it's being pushed to the right? It wants to move down, right? Which way was it moving originally? Oh no, sorry, it wants to move toward you, right? So let's say my stylus is the particle. It's coming out of the page, it's coming towards you, but which way is the force pushing it? The force is pushing it this way, right? So it's going to start to turn. As it turns, though, here's what's happening. Follow my hand. So this is the original setup, right? Just look up. You don't have to do it. Just look up. It's starting to turn. Now which way is my palm facing? Yeah, it's facing toward me, this way. My palm. This way. So it's going to want to move this way now, right? So it's going to start to turn more until it's facing completely toward my arm. Well, now the velocity is to the right, toward you guys. Just look up. To the right, but the force would be toward my armpit, whatever, toward my body. So it's going to start to curl, instead of going left, it's going to start to curl toward me again. So it gets over here. Then which way is the force facing? Yeah, that way. It wants to move this way. So it's going to start to move this way, it's going to start to curl again. So what's it going to do? It's going to start to move in uniform circular motion. And we took this concept of the right-hand rule and we related it to that. So we said, remember that centripetal force due to circular motion is always the same equation. It's right here. mv squared over r. If you don't know this by now, you could remember F equals ma, and this is simply A right here. Right? This is A. That's given on your formula sheet. AC equals V squared over R is given on your formula sheet. So if you forget F equals mv squared over R, just take V squared over R from your formula sheet and say, oh, M times A. F equals MA. That's what you're getting. So mv squared over R is centripetal force. But what's providing the centripetal force here? Remember, the tires on the road keeping it in motion is friction. The planet around the sun, gravity is keeping it. What's keeping this particle in circular motion? What force? What force?
Wait, sorry, this is strong force.
Not strong force for this one.
Magnetic force.
The magnetic force. Guys, take a look. Right? Come on. The reason this particle is curling is because of the magnetic field. So the magnetic force is what provides this. So we have to set these two equal like we did in class. Okay, you need to revisit your notes, please. Revisit your notes. I was hoping you might have seen this. Was it not an example on your problem set? I think there was one with circular motion on the problem set. No? Okay. So set these equal. BQV equals MV squared over R. This is the last example in section 21-3 that we did together. So if you're a little bit lost or a little confused, to revisit that might be useful. What you'll recognize is that this can simplify. Now, in order to do this, we would need to know the type of particle, so we know the charge on it. We would need to know the mass of the particle, or maybe we're finding out the mass of the particle if we know the radius of curvature, or maybe we know the mass of the particle and everything else. We're finding the radius of curvature. Okay, but you're finding one of those above things. But this is the generic approach you're going to take when a particle is moving in circular motion due to magnetism. Okay, due to magnetism. This is how we get particles to accelerate in a particle accelerator by having magnetic fields. Let's see. Like 2 tests ago, I gave an example where a person brushed their hair and the comb gained 7 electrons and the hair lost 7 electrons, right? If I told you that this particle had the charge equivalent to 8 protons, how would I represent that in this formula? If the charge of the particle in this example were 8 protons.
You would do, so be 8 times the charge of it would be 8 times 1.6 times 10 negative 19.
19. Very good. Good memory. Okay, so be careful of that because in the past I've done that and I plan on doing something like that so you recognize the old material still. So when you plug in for Q here, if I tell you that it's like the equivalent of, or let's say it's an alpha particle, I'll say it's an alpha particle. And an alpha particle is just really 2 protons. It's 2 protons and 2 neutrons, but neutrons have no charge, so it doesn't matter. So let's say 2 protons, right? This would be whatever your field strength was, which was 2. That was given in the problem up here in the beginning. You'd have, let's say again, 2 protons. So it would be 2 times 1.6 times 10 to the negative 19. That's what Q would be. The mass of 2 protons, you could figure out. I forget what the mass of 1 proton is, but the mass of 2 protons would go there. Times, let's say we're trying to figure out what the velocity is, and we know the radius of curvature is 10 meters. Okay, we have a particle accelerator with a radius of 10 meters. And let's say our goal is to find out the velocity. This would be given, I don't know it off the top of my head, I forget to be honest, that's why I'm writing it. Okay, but if there were 2 protons traveling in this magnetic field, I'd have double the charge of a proton going in for Q. The magnetic field strength was 2 Tesla. That's given over here on the left, 2 Tesla. You'd have the mass of 2 protons, so I'm writing 2 MP, mass of a proton, whatever that is, times the unknown velocity. We're trying to figure out what is the velocity of this particle that's moving, of this alpha particle, over a radius of curvature of 10 meters. So it really depends on the scenario of the problem that you have to manipulate the formula and the understanding of it. Okay? Questions on magnetism? I'm trying to quickly think if there's anything else. Oh, I talked about hard and soft magnetic materials. I mentioned that, right? What's a hard magnetic material? It's a hard magnetic material.
Something that isn't easily magnetized but keeps its magnetism for a long time.
Yeah. And what is that analogous to? What did I give the example of in class? I said it's analogous, hard and soft magnetic materials are analogous to something. What is it that they're analogous to? What was it?
I'm not sure, but was the gum or was that a different thing?
The what thing?
The gum thing? How it was like some was like is a certain signs that seems to get others? No.
I don't think it was that. I think that's something else. I'm not sure what you mean.
Wait, is it like about the friction thing? Wait, what was the definition again?
Again, magnetically hard materials take a lot to become a magnet, a lot of strength in the field, but they retain their magnetism very well.
Isn't that like a refrigerator or something? Like it takes all the powers up and then it like stays constant.
Well, that's another one. But that was not the one we did in class, but that is similar, the idea. There was something specific that I mentioned in class.
I mean, you talked about space and how like things settle in, so stuff about that and not trying to be magnetic, but I don't know.
Something else.
Is it like airplane? It takes a lot of fuel, so it stays.
Wasn't that? Guys, it's similar to heat capacity. I said, think about chemistry. You did Q equals MC delta T. Remember C was specific heat capacity? For example, you heat up a cast iron skillet. It takes a lot of heat to get it hot. It really does. But if you turn the heat off, it will remain hot for a long time. That's like a hard magnetic material. It takes a very strong magnetic field to make a hard magnetic material into a permanent magnet. But it will remain a permanent magnet even when you remove the magnetic field. Soft magnetic materials can easily be realigned. Their poles, their magnetic domains can be realigned very simply. You take a soft magnetic material, bring a magnet anywhere near it, they automatically realign themselves. But the minute you move that magnetic material out of the way, they unalign themselves, or they, realign or re-misalign themselves, which is kind of redundant. Okay, but they rearrange themselves back into what they were. So it takes a lot of magnetic field strength to make a hard magnetic material a permanent magnet. But once you remove that field, it remains a permanent magnet. A soft permanent magnet is the other way around. It doesn't take much to make it into a magnet, but the minute you move that field away, it becomes pretty much back to its original state very easily. Okay, it's the analogous thing to heating something up. That's what I was getting at in class. Anything else from magnetism that you have questions on? Okay, let's do a mathematical example from the next section. That's what I'm about to do, yep. So the energy levels you're talking about? This one that we did?
Oh yeah. I was thinking chemistry kind of when we said like a reaction that leads to
Show me right after class, okay? I'll get to it. Show me right after class. But no, there's not going to be. But I want to see what you're talking about. So listen real quick. So spontaneous emission. For spontaneous emission, what I want to do is talk about what's physically happening here. Shoot. Okay, in the other class, I did a mathematical example of this, and it's in the video. The stuff that I did in the other class is mainly the stuff that you're going to see in section 23.2, 25.1, and 25.3. Study your quiz. Talk to the class. Study their quiz. Study your notes. Look at your problem set. Okay, highly theoretical, only 2 mathematical portions to this test.